Section: Introduction. In this section, we discuss the ongoing debates regarding the ability of transformers to perform compositional generalization and complex reasoning. We question whether the negative results observed in evaluations stem from training methods or inherent architectural issues. To clarify the limitations of transformers, we propose a framework that helps us understand how these models can learn and represent solutions to various tasks. This framework involves a new programming language called ALTA, which allows us to compile interpretable symbolic programs into transformer model weights. ALTA builds on previous work, specifically a language called RASP and a compiler named Traker. It introduces two main advancements. First, it supports dynamic control flow, such as loops, without needing extra decoding steps, which can be inefficient. Second, it represents the computation of the MLP sublayer using a sparse set of transition rules, allowing us to compile complex programs into smaller transformers, avoiding the combinatorial explosions seen in previous methods. We highlight two main applications of our framework. First, we demonstrate new capabilities for transformers, including algorithms for computing parity and addition, as well as a parsing algorithm that addresses compositional generalization tasks. Second, we provide tools to analyze situations where an algorithm's expressibility is clear, but training does not yield the expected behavior. We suggest using intermediate supervision from ALTA execution traces to guide learning, which can sometimes help achieve the desired outcomes. We also introduce a concept of minimality in programs concerning a training set, showing that non-minimal programs may have parameters that can be altered without affecting predictions. This analysis can predict performance issues on test sets, aligning with our empirical findings. We aim for these tools to bridge the gap between expressibility and learnability in transformers. We are making the ALTA framework available to the community for further exploration. Next, we provide an overview of how ALTA programs are structured, their computational model, and how they can be compiled into transformers. An ALTA program consists of three main components: variables, attention heads, and an MLP function. While we focus on encoder-only transformers for simplicity, ALTA can also be executed in decoder-only contexts. We emphasize that not all computations expressible by transformers can be represented in ALTA, but it effectively supports various deterministic algorithms. The ALTA framework includes both an interpreter for symbolic execution and a compiler for converting programs into transformer weights, ensuring that the output matches the expected results within numerical limits. Section Summary. In this section, we introduce ALTA, a new framework that compiles interpretable symbolic programs into transformer model weights, enabling dynamic control flow and sparse transition rules to enhance compositional generalization and reasoning capabilities. We also discuss how ALTA can provide insights into the expressibility and learnability of algorithms in transformers, offering tools for analyzing training performance and bridging gaps in model architecture. Section: Variables. In this section, we adopt the residual stream perspective of transformers, where the attention and MLP sublayers interact with the residual stream, represented by the activations between these layers. While transformers use vectors for the residual stream of each element, we represent it symbolically as a mapping of variables to values. The variables and their possible values are defined by the program, and we categorize them into three types: categorical variables with limited integer values, numerical variables with real values, and set variables with sets of limited integer values. Additionally, output variables from attention heads can also be null or undefined. We create a one-to-one mapping between variable assignments and activation vectors. Each possible value of a categorical variable corresponds to a standard basis vector, known as one-hot encoding. Set variables use multi-hot encoding, while numerical variables are represented in a single dimension. This mapping establishes a close relationship between the operations of our interpreter and those of a compiled transformer. Next, we explain how an ALTA program executes in the interpreter and summarize how each operation is represented in a compiled transformer, with more details available in the appendix. We denote the value of a variable, for example, foo, for a specific element at a certain sublayer. During initialization, we set every variable at each position based on the input sequence. For the variable foo, we initialize it as a function of its positional index or as a constant, depending on the program specifications. This initialization is reflected in the transformer's embedding tables for input and position values. We then iteratively execute the self-attention and MLP sublayers, which share parameters across all layers. The program can specify a dynamic halting criterion to indicate when computation is complete for an element, or we can set a maximum number of layers to process. Our compiled transformers do not include layer normalization, simplifying the compilation process. In the self-attention phase, we compute a selection matrix for each attention head, which contains weights for input pairs to aggregate information. We assume this matrix is binary, similar to RASP. Each attention head is defined by pointers to query, key, value, and output variables, with specific requirements for their types. Each head updates the value of an output variable based on the defined variables. The selection matrix is generated based on whether the query is categorical or set-valued, and the output values are determined by aggregating selected values. If the value is numeric, we calculate the average of selected values, while for categorical values, the output is undefined if not exactly one value is selected. The interpreter raises an exception for any undefined variable used in subsequent operations. These operations are encoded in the parameters for the query, key, value, and output projections of each attention head. A hyperparameter controls how closely the softmax operation approximates a binary selection matrix. Each attention sublayer includes a residual connection, and we also allow for relative position representations through a binary mask, which is compiled into relative position biases. Section Summary. In this section, we describe how our interpreter represents the residual stream of transformers symbolically through variable mappings, detailing the initialization and execution of an ALTA program, including the iterative processing of self-attention and MLP sublayers. We also explain the operations of attention heads, including the computation of selection matrices and the handling of categorical and numerical variables, while ensuring that undefined variables are managed appropriately. Section MLP function. In this section, we describe the MLP function, which maps a set of variable assignments to a new set of assignments for each element. For our compilation and analysis, we represent this operation as a series of transition rules, interpreted as logical implications with multiple conditions. For instance, when the conditions of a rule are met by the MLP input, the outcome determines the value of an output variable for the next sublayer. Importantly, only one rule can be satisfied for any given output variable at a time. If no rules apply, the output variable retains its value from the MLP input. We also include rules that set every attention output variable to a null value, allowing updates from the next attention sublayer without conflicts. No attention output variable can be the result of any transition rule. We can define the set of transition rules in two ways within ALTA programs. First, we can write a Python function that determines the rules by executing it for all possible variable assignments. If this approach isn't feasible or we want more control, we provide an alternative API for direct specification. The representation of numerical values in the rules is based on discrete buckets for each variable, which helps reduce the number of MLP dimensions needed by focusing on the sparsity of the transition rules instead of creating a full lookup table. The transition rules are embedded in the parameters of the MLP layers. We create a 4-layer MLP with clipped ReLU activations. The first 2 layers convert numerical and set variables into a one-hot representation of their possible values. If only categorical variables are present, these layers can be skipped. The last 2 layers are based on the transition rules, where the hidden activations form a binary vector indicating which rules were satisfied. Each row in the first matrix corresponds to the conditions of a rule, while each column in the second matrix relates to the outcomes. Each ALTA program specifies a categorical output variable. If execution ends after a certain number of sublayers, the program returns a specific output. The dimensions linked to the output variable are encoded in the output projection parameters. The transformer then computes a softmax over this one hot vector and outputs the most likely value. We focus on two main applications of ALTA in this paper, demonstrating new constructive expressivity and analyzing the learnability of algorithms with different training sets and supervision levels. We provide an overview of these applications and our analytical tools, with detailed results in a later section. There has been significant interest in the theoretical expressivity of various transformer classes. However, many theoretical studies do not show specific ways transformers can express algorithms with limited resources, often requiring manual weight specification. Tools like RASP, Traker, and ALTA facilitate these constructive demonstrations. For example, RASP has contributed to new expressivity results for transformers. Much recent work has concentrated on transformer decoders that can perform a variable number of decoding steps before producing an output. While these steps can enhance sequential reasoning, they often need extra supervision during training and may not be the most efficient way to represent certain algorithms. Thus, we find it valuable to explore how transformers can represent various algorithms without relying on intermediate decoding steps. We use ALTA to present new constructive expressibility results for universal transformer encoders under different resource constraints, which we detail in a later section. These results also apply to standard transformer encoders when there is a finite limit on the number of layers. Section Summary. In this section, we describe how the MLP sublayer in ALTA programs maps variable assignments through transition rules, ensuring that each output variable is determined by a unique rule or remains unchanged if no rules apply. We also discuss the expressivity and learnability of ALTA, highlighting its potential applications and the ease of constructing algorithms without relying on intermediate decoding steps, which we explore further in the paper. Section: Learnability. In this section, we discuss learnability in relation to algorithms and transformers. We often find that while an algorithm can be represented by a specific class of transformers, training a model from this class using input-output examples may not lead to a model that performs well beyond the training data. Identifying the reasons for these failures can be challenging, as well as figuring out how to adjust the architecture, training goals, or data to enhance generalization. To address this, we introduce two tools. First, we suggest using intermediate supervision from ALTA execution traces as a learning signal. For a given program and a set of inputs, we execute the program for each input and collect the variable assignments at each sub-layer's input and output. These traces help us derive supervision that aligns the model's behavior with the program's. In our experiments, we focus on training the MLP parameters to recreate the desired output for each input, while compiling the other parameters. We find that this additional supervision can sometimes enable the model to learn the desired algorithm, but in other cases, it reveals limitations in the architecture, such as the type of positional encoding used. We present results on the parity task and details of our training process in the appendix. Next, we complement our empirical findings with a theoretical analysis to understand the conditions under which a specific ALTA program can be learned from a training set. We introduce criteria to determine if a program is minimal concerning a training set, based on whether certain components can be removed without affecting predictions. We focus on the MLP parameters and consider a scenario similar to training with trace supervision, deriving a set of MLP inputs from running a program over model inputs. A rule set is minimal if no rule or constraint can be removed without altering the program's output for some input. We analyze a reconstruction loss that measures how well the MLP outputs match the specified outputs. Our results indicate that if the rule set is not minimal, the compiled MLP parameters do not represent a strict local optimum of the reconstruction loss. Conversely, if the rule set is minimal, the compiled parameters do represent a strict local optimum. Thus, when minimality conditions are satisfied, we can infer the existence of a local optimum that reflects the program's behavior, although we cannot guarantee finding it during training. We can apply this theory to evaluate a specific program, training set, and test set. By identifying a minimal version of the program that maintains predictions on the training set, we can assess whether this version generalizes to the test set. This analytical approach does not require model training or hyperparameter selection, offering a clear evaluation of potentially underspecified program aspects. Our analysis suggests that a transformer trained with trace supervision is more likely to generalize if the minimal program version does. We also relate this concept of minimality to previous work on RASP, noting that certain restrictions on RASP programs align with our criteria for minimality, as we demonstrate in our findings. Section Summary. In this section, we discuss the challenges of generalizing models trained on specific algorithms and introduce two tools to enhance learnability: trace supervision, which uses execution traces to guide model behavior, and a theoretical analysis that identifies minimal program components necessary for effective learning. Our findings suggest that a transformer model is more likely to generalize if the minimal version of the program it learns from also generalizes, providing a framework for assessing program efficiency without extensive training. Section: Experiments and Analysis. In this section, we present our experiments and analysis on various tasks, with additional details and results available in the appendix. For the parity task, we need to determine if a binary sequence has an even or odd number of ones. We have explored how well transformers can learn this task, especially their ability to generalize across different lengths. Previous studies have shown that successful approaches often use scratchpads. We examined 3 ALTA programs for computing parity, which are described in the appendix. The first program, sequential, absolute, checks parity by going through each position and flipping a parity bit whenever it encounters a 1. This program uses absolute positions to share information with neighboring tokens. We also looked at a sequential, relative, version that uses relative positions instead. The third program, sum plus modulo, calculates parity in one layer by counting the total number of ones and then applying a modulo 2 operation in the next layer. We compared the generalization behavior of transformers using these programs, noting that the minimal versions behave differently. The minimal sequential, absolute, program does not generalize to longer examples because it lacks information for unseen positions. The minimal sum plus modulo program struggles with examples that have more ones than those in the training set, as it lacks rules for larger counts. However, it can handle longer examples if the counts of ones were part of the training. Only the minimal sequential, relative, program generalizes across all input lengths. Interestingly, the results from trace supervision match the minimal program's generalization behavior. The sequential, relative, program demonstrates how a universal transformer encoder can provide a length-invariant solution to parity without needing extra decoding steps. We also tested various transformer variants with standard supervision, and while theoretically, a transformer could learn the minimal sequential, relative, algorithm, in practice, all variants behaved similarly to the minimal sum plus modulo program, showing some length generalization but not extending to examples with more ones than seen during training. Next, we discussed the simplicity bias in transformers. Previous research has looked into how transformers might prefer simpler solutions based on complexity measures. For instance, inspired by the minimum description length principle, it was suggested that transformers might lean towards the simplest RASP program that fits the training data. We compared the number of transition rules in ALTA programs to see if transformers show a bias towards simpler programs. Our findings revealed that while the minimal sequential, relative, program has fewer rules than the minimal sum plus modulo program, the behavior of end-to-end models aligns more with the sum plus modulo program, indicating that transformers do not inherently favor simplicity based on the number of rules. Lastly, we evaluated multi-digit addition as another benchmark for transformer generalization. This task has been widely studied, particularly regarding length generalization. Although new positional encodings like FIRE can enhance performance, transformers still face challenges with length generalization unless they receive carefully structured supervision. In the appendix, we describe an ALTA program that can add two positive integers of any size. This program uses a universal transformer encoder with relative position representations, requiring a number of layers based on the digits in the larger input. Notably, the minimal version of this program can generalize to inputs of unbounded length, even when trained only on inputs with a specific number of digits. Section Summary. In this section, we detail our experiments on tasks like parity and addition, highlighting how different transformer architectures exhibit varying generalization behaviors. We find that while some models struggle with length generalization, the sequential, relative program demonstrates a robust ability to generalize across input lengths, suggesting that transformers may not inherently favor simpler programs despite their complexity. Section SUBLEQ. In this section, we discuss SUBLEQ, a simple instruction language that can perform any computation if it has infinite memory. We previously showed how a loop transformer can act as an interpreter for a version of sublec. In the appendix, we present an ALTA program that implements an interpreter for a more flexible version of SUBLEQ using a universal transformer encoder. Next, we address the scan suite, which involves translating natural language commands, like jump twice, into action sequences, such as jump jump. Some training and testing scenarios have proven difficult for transformer models. Successful approaches have often used symbolic breakdowns. In the appendix, we show an ALTA program that tackles the scan task. The program first performs a shift-reduce parsing of the input, creating a tree structure. Then, it generates the output sequence by navigating this parse tree. We represent the necessary data structures, like a stack and parse tree, using a variable number of input tokens. Our compiled models require fewer than 55 hidden dimensions in the MLP, even though there are over 56 possible variable combinations in the program. This emphasizes the role of sparsity, which ALTA achieves by using transition rules for MLP computations. Importantly, our minimal program generalizes well to the test set across the most difficult length-based and maximum compound divergence splits. Thus, our ALTA program for scan illustrates how transformers can represent algorithms that show systematic generalization, allowing a limited set of rules and attention operations to be recombined for new inputs. We also trained various transformer models with standard end-to-end supervision on the same splits, adjusting the number of layers up to 256 for both encoders and decoders, as our ALTA program needs at most 512 layers. However, these models did not generalize well on the test splits, and simply increasing the number of layers did not enhance generalization. This aligns with our findings that end-to-end training fails to learn a sequential algorithm that generalizes effectively, even though such an algorithm can be expressed for a similar class of transformers. Additional results, experiment details, and discussions can be found in the appendix.